Hello everyone. Today we are presenting our group assignment, a deep dive into FishNet with DeepFish and other datasets. Firstly, let's take a look at the architecture of FishNet. As shown in Figure A, the network is divided into three parts: the tail, the body, and the head. The fish tail is an existing convolutional neural nets, for example, ResNet, and the body has several upsampling and refining blocks for refining features from the tail and the body. The fish head has several downsampling and refinement blocks for preserving and refining features from the tail, body, and the head. And then the refined features at the last convolutional layer of the head are used for the final task. Figure B and C are upsampling refinement block and downsampling refinement block. In the UR block, it concatenates the features from body and tail to XSP, and then refine them with convolution M, and then upsample them to obtain the output. The first dataset we use is the popular C400. In C400, there are 100 classes, which are grouped into 20 superclasses. For each class, there are 500 training images and 100 testing images. We use the dataset to test the performance of classification. And the second dataset we use is DeepFish. The dataset consists of approximately 40,000 images collected underwater from 20 habitats in the marine environment of Australia. And we use this dataset to test the performance of classification, fish counting, and segmentation.
Now I'll talk about the classification task and our results of our experiments. Compared to the baseline ResNet 50, we achieve a better performance with FishNet 150 on the CIFAR 100 dataset. On the DeepFish classification dataset, which is a binary classification task, the dataset was too easy for either of the models. And so comparing the CIFAR 100 dataset, we are able to tell that the FishNet 150 is able to achieve better performance, while the DeepFish dataset, we were not able to see significant improvement since the error was already very low. Next, for the counting task, we compare the author's ResNet 50 plus feed-forward network model with torch vision implementation of ResNet 50 on the same counting DeepFish dataset, and we see that the feed-forward network incurs a large number of parameters, but it does increase the MAE performance. Whereas for FishNet 150, we have a similar number of parameters as the baseline ResNet 50, but we achieve better performance than the first two, which shows the importance of the design of the FishNet 150 model, being very efficient with parameters while still being able to deliver good performance. Next.
So next, we did semantic segmentation using the DeepFish dataset. Out of the box, the FishNet 150 is unable to do such a task, but instead we have to add several upsampling and transpose layers to match the label mask. So interpolation techniques such as bicubic and bilinear techniques were used to upscale the output to match the label mask. Next, so the model was able to learn to a very low level of loss. However, the output seems to be very blurry, and that is the case because at the end of the fish head, the amount of details from the output is already very low, and from such low amount of details, we have to upsample and upscale it up to match the label mask, and that is why it becomes such a blurry image, even though it's able to somehow still show the rough area of where the fish is.
Now is the ablation study. The key contribution of the FishNet is the design of the escape connection blocks, UR block and the DR block. The figure in the red shows the UR block, which propagated information from deep layers to top layers and used it to refine the top layers to help with the final task, say equation 4. It can be further break down to 3 steps: the concatenate step, the reduce channel, as well as the refine step, and the upsampling step. Our ablation study wants to test the significance of this concatenating the information from previous layer. So we replace the deep layer by the top layer itself. See equation 5 after ablation. Now, no more other information added, just itself. Note that the channels before and after ablation are the same in the fair of compression. The result in the table shows that this step is quite important to FishNet. Without it, the accuracy on classification tasks, the CIFAR 100 task, dropped by 7.55%. Now we come to the conclusion. In this project, we re-implement the FishNet and apply it to multiple types of tasks. We find that FishNet 150 is a robust model that can perform well in counting and classification tasks. However, the model does not work well on semantic segmentation out of the box. Nevertheless, our experiments as FishNet 150 on the DeepFish dataset outperform the ResNet 50 baseline for counting and classifications. The long-range escape connections, the ablation study, implemented by FishNet contribute to the good performance of the model. That's all. Thank you.